Here's the SAT trap. 4, 5, 5, 6, and 60. One outlier. Which center changes the most, mean or median? To answer that, you need 3 tools: mean, median, and mode. Let's define each one, then you'll see exactly why outliers pull the mean. Mean, median, and mode are the 3 fundamental ways to describe the center of a dataset, but each one behaves very differently. The mean uses every value in the data, which makes it useful but also sensitive. If there is an outlier, like one number much larger or smaller than the rest, the mean gets pulled toward that extreme value. This is why the mean doesn't always represent the data well when the distribution is skewed. The median, on the other hand, is simply the middle value when the numbers are ordered. Because it doesn't depend on all values equally, it stays stable even when the data contains an outlier. That makes the median a more reliable measure when the distribution is uneven or has extreme points. The mode represents the most frequent value in the dataset. It's especially helpful when the data has clusters or repeated values, and it can reveal patterns that the mean and median might hide. Throughout this lesson, we'll see how each measure reacts to different shapes and conditions in the data, and why choosing the right one is essential for mastering SAT math data analysis. This example shows why the mean is easily affected by extreme values, while the median is much more stable. In the top number line, we have a simple dataset: 10, 11, 12, 13, and 14. Both the mean and the median are 12, because the values are evenly spaced and there are no unusually large or small numbers. In this situation, the mean does a good job of representing the center of the data. Now look at the number line below. We take the same dataset and add a single outlier, the number 60. This one value is far from the rest of the data, and because the mean uses every value in the calculation, it gets pulled toward that extreme. The mean jumps all the way to around 20, a dramatic shift caused by just one value. The median, however, barely changes. Even with the outlier, the middle value of the ordered list is still around 12 or 12.5. This makes the median a much more reliable measure of center when the data is skewed or contains extreme outliers. Understanding this difference is essential for SAT math data analysis, because many questions are designed to test whether you know which measure of center stays stable and which one gets distorted by unusual values. This graph shows a classic example of a right-skewed, or positively skewed, distribution. In a right-skewed distribution, most of the data values are concentrated on the lower end, forming a tall cluster on the left. As the values increase, the frequency gradually drops off, creating a long tail that stretches toward the right. This shape has a predictable impact on the mean, median, and mode. The mode represents the most frequent value or interval, so it is found near the tall bar on the left. The median, which is the middle value when all observations are ordered, falls somewhere between the left cluster and the tail. It moves slightly rightward but remains relatively stable. The mean, however, is influenced by every value, including the larger numbers in the tail. Even if only a few values are large, they pull the mean upward, making it the rightmost of the 3 measures. This leads to a key SAT pattern. In a right-skewed distribution, the mode is the smallest, the median is in the middle, and the mean is the largest, mode less than median less than mean. Recognizing this pattern helps you answer many SAT data analysis questions quickly and accurately, even when exact numbers are not given. A bimodal distribution is a distribution that has 2 distinct peaks. These peaks indicate that the data may come from 2 different subgroups, each forming its own cluster. In this example, notice how one group of values is concentrated in the lower range, while another group forms a second cluster farther to the right. Each cluster rises to its own mode, the most frequently occurring value within that group. Bimodal shapes often appear when 2 different populations are mixed together. For instance, test scores from 2 classes taught with different methods, heights of children and adults combined, or reaction times from beginners and experts. The key idea is that the data is not centered around a single typical value, but instead shows 2 areas where values are common. Understanding a bimodal distribution is important in SAT data analysis because it warns you that a single summary measure, like the mean or median, may not represent the data well. Instead, recognizing the 2 clusters helps you interpret the real story behind the numbers. By identifying the 2 modes and noticing the gap between them, you can infer that something meaningful is separating the groups, making the distribution far more informative than a single peak pattern. A small dataset allows us to clearly see how value, frequency, and cumulative frequency work together to describe data. Here, the values appear multiple times, and frequency tells us how often each value occurs. For example, the number 12 appears 3 times, making it the most frequent value in this dataset. Cumulative frequency builds on this by showing how the total count increases as we move through the values from smallest to largest. This helps us understand the position of the median, because the median is the middle point of the cumulative count. In this dataset of 7 values, the median falls at the 4th position, which corresponds to the value 9. The mean gives us the numerical average, which comes out to about 8.9, slightly below the median because the highest value appears several times and pulls the distribution upward. And the mode, the most common value, is 12. Together, these measures, mean, median, and mode, along with frequency and cumulative frequency, provide a complete picture of how the data behave, even when the dataset is very small. Before we move on, let's connect what we've learned, mean, median, and mode, to a real data visualization. A histogram shows how data are distributed, and the overall shape of that distribution affects how the center behaves. This matters because the SAT often combines histogram questions with concepts like mean, median, and mode. So understanding how to interpret the graph is an essential skill. Here, we have a typical SAT-style histogram. The data are grouped into equal width intervals or bins, which is always required for a proper histogram. The height of each bar represents the frequency, in other words, how many values fall within that range. Notice how the bars rise toward the middle and then decline. This pattern gives us a sense of where most data are concentrated, which helps us estimate the center of the distribution. For example, if most of the height is around the 20 to 40 range, we know the mean and median will likely fall somewhere in that region as well. Histograms don't tell us the exact values, the way a raw data list does. But they show the overall shape, which can reveal skewness, clusters, or outliers, all of which influence the mean, median, and mode differently. By learning to read this shape at a glance, you'll be able to answer SAT data analysis questions much more confidently and quickly. Let's take a closer look at how a single outlier can dramatically change the center of a dataset. In the upper dot plot, we have the values 5, 6, 7, and 8. They are tightly grouped, and both the mean and the median sit around 6.5. Because the values are balanced on both sides, the mean and median align closely, showing a stable center. Now look at the lower dot plot. We take the same 4 values, 5, 6, 7, and 8, but this time we add one extreme value, 40. This single outlier sits far to the right, and it heavily influences the mean because the mean uses every number in the dataset. As a result, the mean jumps all the way to about 13, even though most of the values are still clustered near 6 or 7. The median, however, hardly changes. It moves from 6.5 to 7, because it depends only on the middle value or middle pair of values, not on extreme values. This illustrates one of the most important ideas in data analysis. Outliers affect the mean much more than the median. Understanding this difference matters on the SAT, because many questions ask you to predict which measure of center will shift, and how much, when an outlier is introduced. So whenever you see a dataset with one value far away from the rest, immediately consider how strongly the mean will be pulled in that direction, while the median remains much more stable. Box plots are a powerful way to visualize how data is spread, especially when comparing datasets with and without outliers. In the first box plot, using the values 5, 6, 7, and 8, all the data points sit close together. As a result, the box is narrow, the whiskers are short, and the median sits right in the center at about 6.5. This creates a compact and balanced picture of the dataset's distribution. Now look at the second box plot, where we add a single outlier, the value 40. The main cluster of values, 5 through 8, still forms the box, and the median shifts only slightly to 7. But the outlier dramatically stretches the upper whisker far to the right. Even though only one value is responsible, the entire visual range of the plot becomes much larger. This shows how outliers influence the overall spread and can make the dataset appear more variable than it truly is for most of the values. A key takeaway for the SAT is that box plots make outliers visually obvious. They highlight how a dataset's spread can change dramatically even when the center, represented by the median, barely moves. So whenever you interpret a box plot, pay close attention to unusually long whiskers. They often signal the presence of extreme values that significantly affect variability. Let's take a moment to review the key ideas from the first half of this lesson. We began by exploring the 3 major measures of center: the mean, the median, and the mode. Each of these tells a slightly different story about the data. The mean uses every value and therefore moves a lot when extreme numbers are present. The median, however, depends only on the middle position and stays stable even when the data includes unusually large or small values. And the mode highlights repeated values, showing clusters or common patterns within the dataset. We then examined how outliers can distort our interpretation. A single extreme value can pull the mean far away from the rest of the data, while the median barely moves. This is why understanding the impact of outliers is essential, especially on the SAT, where subtle changes in the data can lead to very different conclusions. Next, we looked at distribution shapes. Right-skewed, left-skewed, and bimodal distributions each shift how we interpret the center and spread, and they often reveal deeper patterns in the data. Finally, we used dot plots, histograms, and box plots to visualize these ideas. These tools make patterns easier to see and help confirm whether the mean, median, or mode is the most reliable measure to use. With these foundational ideas in place, we're now ready to move into the second half of the masterclass, where we'll apply these concepts to SAT-style questions and real test scenarios. Here is your intermediate practice problem. Take a careful look at the histogram and decide which statement must be true based on the data shown. Pause the video now and take your time. To solve this problem, start by looking at the height of each bar. The tallest bar represents the interval from 20 to 30, which means this is the most common range of values in the dataset. That directly supports answer choice C. Answer A cannot be guaranteed because a histogram does not show exact individual data points, so the median's location cannot be known precisely. Answer B is also uncertain. We cannot determine the exact relationship between the mean and the median from a histogram alone. Finally, answer D claims strong right skew, but the histogram here does not clearly show a long tail on one side. Therefore, the only statement that must be true based on the histogram is that the most common values fall between 20 and 30. Here is your advanced practice question. Study the histogram and consider how adding a single outlier affects the mean and the median. Pause the video now and work through your reasoning. In this problem, the key idea is understanding how the measures of center react to an outlier. The median depends only on the middle value of the ordered list. Adding one extremely large value, such as 80, does not change the middle position much, so the median remains almost the same. The mean, however, uses every number in the dataset. When a very large value is added, the total sum increases significantly, which causes the mean to shift upward. This makes answer A the correct choice. Answer B is incorrect because the mean and median never move by the same amount when an outlier is added. Answer C is incorrect because a mode must be the most frequent value, and a single 80 cannot become the mode. Answer D is incorrect because an extreme high outlier pushes the mean above the median, not below it. So the correct conclusion is that the mean increases significantly while the median remains nearly unchanged. In this lesson, you learned how to interpret histograms, how to understand the relationship between mean, median, and mode, and how outliers can dramatically change the story told by a dataset. You also saw how distribution shapes, such as skewed or bimodal patterns, influence which measure of center is most informative. These concepts appear frequently on the SAT, not just as definitions but as reasoning questions that require you to understand how data behaves. By practicing how histograms connect to center measures, and how outliers shift the mean much more than the median, you now have a strong foundation for tackling real SAT data analysis problems. Keep reviewing these ideas, and you'll be well prepared for the test.